Alright, hey, what's up guys, it's Fod, and we're going over top interview questions, medium set, linked list. Question number 3, intersection of two linked lists. So given the heads of two singularly linked lists, heads A and head B, return the node at which these two lists intersect. If the two linked lists have no intersection at all, return null. So in this case, go through A and B and you see that they intersect at C1, right? The node C1. Over here, they intersect at node 8, so you just return 8. Over here, they were intersect at 2. Over here, they don't intersect, so you return null. And they give you a whole bunch of constraints about the elements in list A and list B. Yeah, so I want to give you guys the first solution that came to mind for me. So this solution was a pretty simple one where you use a hash set. So you may be thinking, Fod, how are you going to use a hash set for list nodes? Because list nodes are defined recursively by defining the next one, right? So you're thinking, how much space would you have to allocate in each position? The data structure wouldn't know. You can't make like an array of list nodes. And the thing is, you can. The thing is, with Java, they don't really let you discover yourself the concept of pointers. So pointers is basically it's an address to the object. So for a hash set, you need to know the size of the object you're storing. So if it's an int, it's 64 bits. And 64. All right. And if it's a char, it's 8 bits. And this basically tells the hash set how much space it should allocate. So hash sets, I think they originally have a size of like 10, but whatever. It tells you how much space you should allocate for each integer. But if it's a list node, it could be defined recursively. It could be a huge length. You have no idea how much space you should allocate. So most of the time, well, actually all of the time, when you have an object, Java actually converts it to an address when it's using a data structure. So even though it says list node here, it's actually storing a pointer to a list node. So that's why it's really important. You should learn concepts such as pointers by picking up C or C++, which are also very useful languages. So that's the idea. You go through one linked list and store all the pointers that you see, all the nodes that you see, and go through the second linked list and see if you find any values in that hash set. And that's exactly the solution I have over here. So over here, I go through list A, and I store all the nodes. So I add to a hash set. And then I go through list B and check if the hash set contains any of the same nodes. So if it does, that means that there's an intersection, right? And then you just return the node where you intersect that. Otherwise, you just keep on iterating through and return null otherwise. So let's see the situation. So over here, you iterate through A, you store 1, 9, 1, 2, 4, these nodes. I'm really storing the addresses, but who cares? And in list B, you go through 3, and then you see 2 2s in this hash set. So you can return the list node 2. Perfect, right? So, but the follow-up is, could you write a solution that runs in O(n) time and only uses O of 1 memory? And this is the actual interesting part of the problem. Otherwise, this problem would be pretty trivial. So for this problem, there's two aspects. There's the list A and list B, which are the two singly linked lists. So the two aspects are the lengths. So either they're equal or not equal. Equal lengths or not equal lengths. And the second one is whether they intersect. So that's just a yes or no. And with this, you can get your 4 cases. So the lengths are equal and they intersect and they don't intersect. The lengths are not equal and they intersect and they don't intersect. And when you're doing these coding problems, it's usually hard to think of the solution like right away. So it's always good to do examples, and with that you can think about solutions along the way. So we have 4 cases. Let's go through these 4 cases. So if it's the same length and they intersect, you can just move the pointers one by one. A, move B, move A, and then move B. And eventually they'll intersect, and once A is equal to B, so while A is not equal to B, you want to move these pointers up one by one. And once they're equal to each other, then you can just return that value. Okay, so that's the first thing, first case, which is same length and they intersect. So now let's look at the next case. Same length, equal length, and they don't intersect. So if they're the same length, you just move them one by one. A moves to A2, B moves to B2, and A and B are list iterators. So they're just going through the list. They're not actually changing anything in the list, which was one of the conditions that they stated they stated that linked list must retain the original structure after the function return. So you're just iterating through it, you're not actually changing anything. And another important thing is that there's no cycle. So eventually you'll reach null, like in this case. So you move one by one and you reach null. And null is equal to null in comparison. So you can break out this loop and return null. That's our second case. I don't know why it says 3, but basically that's pretty simple, right? You can just, so far we've just been moving A one by one and B one by one together. Why? Because they have the same lengths. So what's actually the hard part though about this problem is when they have different lengths. So the case I'm going to go through first is different lengths and no intersection. So A moves to A2, B moves to B2. A moves to A3, B moves to B3. A moves to A4, B moves to null. So what we do here, this is usually this point that we stopped in the last two cases, right? Either they intersect or reach null. What can we do here to make it so that they reach a similar point? Because we want to show that there's cases where they do intersect, that one will reach null first, right? So we want to somehow make it go through the same length and then show an intersection. So how do we do this? We have B go through the list of B and the list of A. So if this is 4 elements and this is 5 elements, it'll go through these 4 elements and then these 5 elements. So if they're going through the same length, and A will go through these 5 elements and then these 4 elements. So if A and B are going through the same amount of values, right, one by one, so if they're both going through 9 values, eventually they'll end up at the same point, which is an intersection or null, right? So when B is equal to null, move B to the head of A, and then A moves up here, then B moves A moves to A is equal to null, so move A to the head of B and move B forward. And now we can stop here. So this went through 4 elements and this went through they both went through 5 elements, right? But now the distance from null is the same amount, which is 3. And that's perfect because then you can just move them one by one and you'd see that they reach null at the same time. And A is equal to B, so you can break out. So essentially they both went through these 1, 2, 3, 4, 5, 6, 7, 8, 9 values. They both went through 9 values and reached the end where they got a comparison that they're equal to each other, and you break out, return null. So can we extend this idea to different lengths and they do intersect? And the answer to that question is yes. So over here, this has a length of 1, 2, 3, 4, 5, 6. This has a length of 1, 2, 3, 4, 5, 6, 7. So move A to A2, move B to B2, move A to C1, which is the value they should have intersected at, move B to B3. Move A to C2, move B to C1. And they both move up 1 again. One sec, there we go. A moves to null, B moves to C3. And same idea, we move A to the head of B. And then we move B to null. Then A moves forward. And B moves to the head of A. So what did we essentially do? We took the long and linked list and we ignored the first value. Why? We ignored the first value. Why? Because the difference in the length of these two linked lists is 1. So when A went through like the elements M, when A went through M elements, it also goes through, B goes through N, right? B goes through N elements. But since we're moving them one by one, A is also going through M minus N elements in B. A is going through M minus N elements in B. So, no, N minus M, my bad. So in the end, the distance from null for both of them reaches the same. Why? Because they're iterating at the same pace of 1 by 1, and they're going essentially through both linked lists. Just like the example where they don't intersect, we went through all the elements, but in this case, we're going through both linked lists, and this way, the difference in their lengths is made up for in the beginning, and you can just move A and B 1 by 1. And eventually, look at that, C1, they both reach C1 at the same time. So you gotta really understand why the solution works. It's because it's going through one linked list and then the other, and the difference in length is accounted for by them both moving at the same pace, and it going through one, then the other, and basically vice versa. A goes through all of A, goes to B, B goes to all of B, goes to A, and then eventually, even if they didn't reach C1, they'd reach null at the same point. And they're both equal to C1, and you can just return C1 at that point. So those are the 4 cases. So this solution was by Brian Bocow. Hope I'm saying that right. I saw it on Leetcode discussion board somewhere. It's a really smart solution. He was the one who came up with these examples, and I'm just explaining it. So always like to give credit where credit is due. So go check him out. He's on Leetcode, I think. But he doesn't make videos. He just made a discussion board solution. So now let's talk about complexity. So space complexity, O of 1. Why? Because A and B that we had before are just list iterators. No matter how long these linked lists are, they could be like 100 elements, right? You only need one iterator for A and one iterator for B. So space is not dependent on the number of elements, N or M. So list A length is equal to N dot length so the space is not dependent on M or N. That's why the space complexity is O of 1. As N or M changes, the space doesn't change at all. Now let's talk about the time complexity. So in the worst case that we saw was case number 3, where we went through 2 linked lists that had different lengths and they did not intersect. That means you went through both iterators had to go through both linked lists. So that's O of N plus N. So go through all the elements in list A, then all the elements in list B, and they both reach null at the same time, which is simplifies to O of N. Or O of N or O of M, whatever. They're just N and M. It's not N squared or anything like that. So with that, we got the follow-up solution, and now let's just try coding it up real quick. So let's scrap this little solution. This little solution is useless to us now because we got a better one. So first things first, let's check if head A is equal to null or head B is equal to null. Because if one of them are equal to null, you just return null, right? There's no intersection. And returning a list node. So list node either is the value that you intersect at or null because you haven't found anything. So while, oh wait, first let's make our 2 iterators. Oh wait, let me make this bigger for you guys. It's kind of small. There we go. So list node A is equal to head A, and this is iterator. Make one for B2. Oof. And while A is not equal to B, what do you want to do? If A is equal to null, you want to move it to the head of B. And otherwise, you just want to move it up. Same idea with B. You know, I'll just copy the code. Make my life easier. So if B is equal to null, you want to move B to the head of A. There's actually a way you can do this in one line, this whole if case thing. But I kind of forgot. I don't want to search up the syntax. So basically, if B is equal to null, you want to move it to head of A. Otherwise, you want to move B forward. It's just like the 4 examples that we talked about. And in the end, this will always result in a case where A is equal to B, either if it's the null case or the point where they intersect. And over here, you want to return A or B. You can return either or because they're going to intersect because A is going to be equal to B when this loop finishes, right? File error. Oof. Head B is equal to null. Okay, so our answer was initially correct. Let's submit it and see our solution. All right, that's great. Our solution was accepted. Thanks so much for watching. If you guys have any recommendations or suggestions, leave in the comments. The code is always in the description and the GitHub link, so look out for that. I'll see you guys in the next video, and this is a list B iterator. Thanks so much for watching. I'll see you guys in the next video.